the title of this talk is AI, the Past and the Future. And the goal of this talk is actually to share with you some thoughts about trying to address the following question: what AI would look like, at least in Africa, or in particular in Africa. Of course, you cannot predict the future, but if we cannot predict the future, maybe I can at least share with you what I would like that future to be, AI in Africa. But I'm somehow convinced that it is hard to think about any future without understanding the past. So of course, I will try to share with you what I believe the past has been in this area, and then share with you my thoughts about what a future, at least a nice future, could look like for Africa. So these are the two parts of the talk: the past and a future. And of course, the time I will be spending discussing with you some historical aspects of the past of AI are biased towards what I believe, what I want the future to be. So what is AI? And this is something that is, I find very intriguing question to discuss with people, especially in Africa or in Morocco in particular. People have different views of what AI is, and sometimes these views can be dangerous, and I will try to explain that. So the way, one definition of AI I just cooked up this morning is the following: is the ability of a non-mathematician to solve a problem that only mathematicians believed they could solve. Okay, so only mathematicians believed they could solve something, and suddenly non-mathematicians are able to do it as well. And they do it in a rather artificial manner because they are not mathematicians, so they don't really understand what they are doing, yet they are solving the problem. And I think that definition, although it was not expressed like that, has been somehow has been valid in the past. A long time ago, somebody called algorithm was asked to educate the people in Baghdad, and in particular to educate the non-mathematicians and to help them solve difficult mathematical problems. And one difficult mathematical problem at that time was to sum two numbers. And that was considered very difficult because the numbers were represented by Roman symbols. And if you think of how to sum with Roman symbols, especially big numbers, it's a nightmare. So few mathematicians knew how to do that, but the vast majority of people of Baghdad had no clue how to do it. So what he did actually was to invent a way to represent the numbers, to data representation model that was somehow amenable to an algorithm or a procedure that would enable anyone to actually be able to do the sum without understanding why precisely that representation model was good and why the algorithm we all do today, including kids, work. Like, why is it that when you go over 10, you keep that one aside and then you add that one later and then you move to the left, etc. So that was a definition that actually was pretty, although not expressed that way, but people used to talk about some artificial way of solving a problem without really understanding it. But that was some time ago. And algorithmy didn't only propose a recipe for summing numbers, but he proposed also recipes for solving second-degree equations, multiplication, etc. And the common pattern is that non-mathematicians were able to solve those problems that were somehow reserved for mathematicians. But of course, people were doing that without thinking. This is what I try to explain. They didn't understand why it worked, but they applied the algorithm's recipes and it worked. So they were somehow behaving like machines. And a few centuries later, some great inventors basically sat down and thought, well, if when we do those procedures, when we execute those recipes, we don't think, we execute them like machines, maybe we can have machines actually execute them. And this is, for example, what Pascal did a few centuries later. Blaise Pascal invented a machine to actually execute algorithmy's algorithm. The sum algorithm proposed by algorithmy was somehow hard-coded in Pascal's machine, and that algorithm was able to execute sums clearly without understanding what was going on. What is interesting is that at that time, people started really talking about artificial intelligence, because for them, for people of those times, only human beings were able to do additions, to execute sums. And we know from algorithmy that in fact, only mathematicians used to know how to do that. But then everybody was able to do that, but it was something that only humans used to do. And after Pascal, people started talking about something artificial. In fact, according to the legend, the church decided to burn the Pascal's machines because the church considered those machines to be acts of devil, because only humans could do mathematics or addition. And if a machine would do that, then there was something weird, something against religion. But the definition that I was talking about, which is an ability of a non-mathematician to solve a problem, somehow has been transformed into the ability of a machine to solve a problem that only humans believed they could solve. Of course, today, this would not be called AI, right? But it has been called so at some point in history. And this happened over and over more recently. First, when people started playing chess, when machines started beating people in chess, especially the world champions, we started talking about artificial intelligence. Deep Blue in 97, same for Jeopardy, when machines started beating humans in Question pour un champion, or Jeopardy, which is the American version. Many newspapers said, oh, this is artificial intelligence, because a machine was able to understand the question, analyze the question, digest the question, find the solution, reproduce somehow the sentences to make the people understand the sentence. So this was called artificial intelligence. But maybe today it would not be called so, because that was already 10 years ago or 11 years ago. Same for painting. People initially believed only a human would be able to reproduce, to do some art activities. But we know today that algorithms are able to reproduce some of the best, to mimic some of the best painters. Today in Lausanne, there is, I think it's today or tomorrow, there is the 10th Symphony of Beethoven played by machines. Okay, so this would be called artificial intelligence, but maybe in 5 years, it won't be called so. Why? Because we would have realized that actually it's not only humans who can solve those problems, poker, etc. It's not only about games, driving, medical activities, etc. So this idea that there have been activities that only human thought they will do and then machines replace them is somehow, in my view, what artificial intelligence is. What happened that was also very interesting in this somehow wave of new exploits of machines is the fact that the first machines, like the one of Pascal and some others, were only doing one thing at a time. Pascal's machines was only doing additions. It was not doing other things. But then some inventors went to go further and to mimic humans in their ability to learn new algorithms. Okay, Pascal's machines was not able to learn new algorithms, executed only one. There was another machine during almost the same period by Leibniz, which was only doing multiplication. It was not able to learn a new algorithm. Some inventors tried to build machines that learn algorithms. And this is the picture of Ada Lovelace, which was actually trying to build a machine that would learn new algorithms. Of course, she died. Of course, some of you know that she died too early to build her machine with such baggage, but still the ideas were there. I'm using this this part of the history to highlight the fact that women have been instrumental in this field of computer science and artificial intelligence. It's not only a human field. Until Alan Turing came and invented or drew the plan or the model of a machine that would learn new algorithms, and therefore that would be able to execute activities that only humans were able to do. So Turing's machine was able to execute, to learn and execute various algorithms, Pascal's algorithm, Euclid's algorithms, algorithmic second order equation, etc. So that was something fundamental, somehow in the history of AI, or as I will explain in a minute, in the history of computing in general. So of course, when Turing died, as you all know, people started building machines. It was about 54. IBM 650 was somehow built and started being sold at that time. And the wave of computing started invading the world. But what is important here is that this notion of exploit of computing is related to the addition of two things: algorithms as invented initially by algorithmy and others, plus machines. And the combination of these two has given birth to a new science or a new discipline that we call today computing. So computing is the addition of mathematics and technology. And AI is an exploit, prouesse, of computing. Of course, the notion of prouesse or the notion of exploit is very transient. At some point, something we call exploit, but then 5 years later, it's not anymore. The reason I'm saying that is precisely because I believe that what matters is the field of computing. What we call AI is not important, in my opinion. What is important is this field of computing that is progressing, and whenever this field impresses us, we talk about AI. So the combination of these two subfields of computing, mathematics and machines, is somehow at the foundation of this amazing discipline that seems to be impressing us every now and then. And we use the word AI somehow to say that this is something surprising. So the keys to success to AI or to computing in general are algorithms and machines, and more precisely, networks of machines as invented by Turing. If machines were not connected among themselves, they would not be able to compute fast and to store a large amount of data. So somehow AI and the exploits of computing is due to the mathematics of algorithms as well as to technology, machines, especially machines that can be connected. And as we know, there have been two revolutions in the way we connect machines: the infinitely small revolution, where we connect several machines within the same processor to gain speed, as well as the infinitely big revolution, where we connect machines for high availability to access data, etc. So these are the two ingredients, distributed Turing machines and algorithms, that somehow lie at the heart of computing and its exploit. And this is what makes these new industries so flourishing today. If you go spend some time in the research centers of these groups or in the development centers of these groups, then you will see that what people actually do is algorithms plus distributed machines or distributed networks. This is what happens there. So now, why am I telling you that? I'm telling you that because I believe that understanding this past might help us not necessarily predicting the future, but maybe actually predicting it by building it, by cooking it up. And the first element that I wanted to emphasize is the fact that AI is nothing more than a successful combination of mathematics and technology. Believing that somebody could become a genius AI researcher without understanding technology and only by doing some statistics, in my opinion, is a mistake. Similarly, if somebody just understands technology without really understanding what algorithms are and what the field of algorithm is, what is complexity, etc., in my opinion, is also a mistake. So any education towards artificial intelligence has to involve these two components. So what do we call AI today in industry? Is either, I'm simplifying a bit for the sake of my talk, and the reason I'm doing that is now I'm starting to suggest some areas for the future, in particular for young researchers who may work on this field in the future. So today AI is PyTorch, TensorFlow, is basically this picture today. Roughly speaking, there is some parameter server somewhere, a machine that collects some models, aggregates some elements of learning by other machines and build a new model out of that, and then redistribute that model to the machines that will learn from data, come back to the machine, etc. Those of you who are familiar with SGD know exactly what I'm talking about. Those who are not familiar with SGD, it doesn't matter. What is important at this point is to somehow, I hope, agree with me that this is, roughly speaking, the state of the art of today's AI. Of course, this model here of one parameter server may be located at some cloud with some workers, as we say, may be located at the same cloud or maybe located at the customers of this system. They might be mobile phones, are challenged. This model is challenged, and it's challenged by several things. One of them is data, that the amount of data keeps increasing. The second thing, of course, is that those who are producing this data and those who are customers of this architecture that I presented seem to be more and more concerned with sensitivity of their data. This is something that we keep hearing, and maybe, and I really hope that people will really be at some point worried about sharing their data. But there's also an interesting phenomena that is pretty recent, and now again technology comes to the picture, so there are always these two aspects, is the fact that the mobile devices, because these are the machines that are producing data, are becoming more and more powerful, and there is a large number of them. Okay, the number of mobile devices, maybe we're reaching 4 billion or something. It is just crazy, and this might lead to a future where we would go from this model that today somehow is the privileged model for Google and Facebook and others, towards this model where instead of having one parameter server and several machines and several workers, we would have a completely distributed, I call that genuinely distributed learning, or some people call it decentralized learning. I hear some noise. I hope it's only me who is hearing that noise, but that's okay. If it's only me, it's fine. This future might be very challenging. It is very appealing because this would mean that we would not need to go through intermediate servers somewhere, in particular in big GAFAM giants or whatever. But in a continent like Africa, it might mean a completely distributed a distributed way of learning that is really decentralized. And this might raise several interesting research directions, in addition to also okay, I'm hearing some noise. I hope it's okay. So let me give you one example of interesting problem. If you go to this picture of completely decentralized learning, which might somehow be fantastic for a continent like Africa, where the number of mobile phones is increasing. Let me give you one example where we have interesting research problems that researchers could work on. There are two threats, essentially, when we go to this completely decentralized model. These threats are actually already there in the current model. Let me just say a few words about that, and this will be my conclusion, just to give you an example. So in the current model, we have one parameter server and a bunch of workers. We tend to consider or to assume that these workers are honest, that they will do the work correctly and send back a good answer to the parameter server, which averages all the gradient sent. Sorry for the jargon. If you don't understand it, that is not important. What is important is that as soon as we want to be really technology aware and we realize that in fact those machines might not be correct, we go from theory to practice, then averaging is not good anymore, because averaging can be manipulated by a single worker, which gives a completely crazy data, sometimes talk about poisonous data, and corrupt the entire learning. Similarly, and as I pointed out, this parameter server could also learn things about the workers, and this is another threat. What is interesting is that these two threats have been tackled in the recent past. People have been proposing solutions to each of these. But when you put them together, and this is a very recent result of ours, I'm just giving you one example, when you try to handle what we call Byzantine failures together with somehow privacy, or what we call differential privacy, you realize that the two techniques that have been used recently don't add up. You cannot put them together. And again, this happens because we have somehow tried to combine some results from a theoretical perspective, from mathematics, with somehow concerns about technology. And the result is an interesting impossibility that I believe could lead to amazing research direction. And this is just one example. So what I'm trying to say is that going to a completely decentralized learning, for example, using only all mobile phones, which might make sense in a country like Africa, would not only lead to interesting economical model, but also to interesting research problems. So this was just an example. For those of you interested in other examples, I can point you to some papers that we have written in my group in Lausanne with the great PhD student and postdocs. I'm not mentioning them here, I apologize, but those were the main researchers who did this work. Okay, so thank you for your attention. I went slightly over time, maybe 2 minutes over time. Sorry about that. And if there are any questions, I'm very happy to answer.
Thank you very much, Professor Rachid. We have a question about addressing the AI topic in this manner. Would addressing the topic in such a manner simplify the barrier of entering the field for other people?
Very good question. Absolutely. This is one of my motivations of explaining AI in that way. Because if you explain AI by directly going through statistics or by directly going through some specific applications, technological applications, I think you lose, not only you lose people because they don't understand you, but maybe you lose their interest. I think it is very important to equate AI with the more general area, which is computing, which is a scientific field.
You've discussed that the current state is the distributed learning. And in my field, so I work a lot with medical data, and we see that there is a struggle in publishing this data in a distributed manner. Could you give us an insight? Why is that the case?
Yeah, so it's very good comment, because there is a trade-off between trying to make sense of medical data and, for example, trying to predict some diseases, etc., and hiding or protecting that data. Because once we want to make sense of the data, we have to distribute it over several machines, for otherwise we won't be able to somehow treat it locally, and people don't want to share the data. So how can we benefit from each other's data and information without stealing or without giving those information to some companies that might badly use it? And this is a very important challenge, because encrypting is sometimes too heavy. Ensuring, as I pointed out, some form of differential privacy doesn't go well with protecting security. So there is an important research challenge that today we don't know how to solve. So it's a bad news for those who want to help us cure diseases with AI, but it's a fantastic news for researchers who have to work on this topic.
I agree with you. Well, it's some bad news for us, I would say, working in that industry.